In today's episode, we're going to take a look at a common interview question, break it down into different parts, and then try to implement a solution. Let's go! Today we're going to take a look at an interview question, and it's a pretty common one. It reads as follows. A prime number is a natural number greater than 1 that cannot be formed by multiplying two smaller natural numbers. Write a function that prints all the prime numbers between 1 and n. The first thing you may notice is this is very mathematical. And it kind of makes sense if you're coming from a computer science background where you do a lot of math as well as programming. But if you're more self-taught or coming from a boot camp or something like that, you might feel a bit uncomfortable. And we'll try to break down some of the terms here to make it a bit more understandable. It says a prime number is a natural number. And what a natural number means, it's an ordinary number that you use to count, like 1, 7, 55. 1, 2, 3 are all natural numbers. Usually you don't include negative numbers, like -7 would not be a natural number, or numbers containing decimals like 3.14, 5.59. So just normal everyday numbers. It's greater than 1, we can work with that, and it cannot be formed by multiplying two smaller natural numbers. So if we can take two numbers like 5 and 10, multiply them together and get 50, we know that 50 is not a prime number. Write a function that prints all prime numbers between 1 and n. This is also a notation that's kind of mathematical in nature. What it means is that if we give our function a number, it will loop over all the numbers between 1 and this number, and if it's a prime, it will print it. Let's see if we can build something that satisfies this question.
So I've created this project where we can work. First of all, I added Jest as a testing framework and a script to run it for the project. Then I went ahead and created our file, which has a function called getPrimeNumbersBetween, which takes a number as a start value and a number as an end value. So this is the function that we'll use to give it a start value like 1 and an end value like 10, and then it will return an array of all the prime numbers between 1 and 10. Then I went ahead and created a test file, just so we know that our function actually does the thing we want it to. We have our function getPrimeNumbersBetween, and it should return the prime numbers between 1 and 42. So we call our function with 1 and 42, and then we expect the result of this function to equal this array of prime numbers that I found on the internet, so we know they're correct. Creating a test for this kind of function, I find it really useful, as for these kind of problems where you have a super well-defined input and output, just going ahead and start by creating your function with an empty body and then adding your test. It gives you a great tool, because then you can add all the different output and inputs you expect, and then you can do changes, you can start implementing, and you can see like how well are you doing, how close are you to the solution. You don't know that you don't do a change and just break some edge case. And especially if you don't really know how to approach a problem, having the test there, you can kind of try things out, and you see like, oh, it works in these cases, but in this case it don't. Okay, then we have to take that into account, etc., etc. So if I run the test now, we'll see that it fails, and after we give it a minute here, we'll see that it respected this array and we got an empty array. So we can close the test file and go over to our implementation. So what we want to do here is create a list with our prime numbers. I'm going to return this instead of this empty array. Then we will want to do a normal loop to loop over the values we have and see if each one of them is a prime number. Here we start at our beginning, which is 1 in our test case, go up to 41. Then we check if this number is a prime, and if it's not, we go ahead and skip to the next one. If it is a prime, we add it to our prime array. Could write this as a true value here and add it inside the if statement, but I prefer using early exits and just getting the cases that's not valid out of the way first, and then you can focus on your primary code. In this example, it doesn't make that much of a difference, but when you start having more logic and more condition, it's a good practice to try to exit out of the function as early as possible. As soon as you do know something is not a valid case, so you can just forget about it as quickly as possible. We'll take that approach here when we define the function is prime, which takes a value or a number even. And here we can start off by just return true. Okay, every number is a prime. But then we have our definition, right? We know that, for example, if it has to be a prime number has to be greater than 1. So we can do if number is less than 2, return false. Now we see that we get a lot of numbers in here. Some of them are okay, some of them not. So now we just have to keep working on this definition of its prime number until all the numbers in red disappear, so we only have the white ones left. Looking back at our definition, we can see it has to be a natural number. So if it's not a natural number, we can go ahead and return false as well. We said that a natural number is a number without decimals. The easiest way, in my opinion, is to take the number and use a rounding function and check if this is the same as the number we passed in. Then we know that this would be something like 37.7. Then the rounded version would be 37, which is not equal to 37.7. But if it's 42, the rounded version would be 42 and would have a match. It won't really help us in this case because we only have positive numbers. The first approach we can take is to just look at all the different combinations of numbers and see if it results in our target number. So we could do a double for loop, starting with 2, I guess, where a is smaller than the number we have, and then we do the same thing, but we replace what would b, and then we do result equals a times b. This will go through all the numbers between 1 and 7 in this case maybe, and then we'll just see if there's a combination. And if the result equals number, which is our target, we return false. This is not a prime number. And all of a sudden we have a working solution. And this solves our problem. The thing though is that what we need to realize is that this function, as we have a double loop that's based on the number we put in, the bigger this number gets, the slower it's gonna get, and it will grow exponentially. Because say that we pass in the number 10. This loop will run 10 times, but this inner loop will run 10 times for each one of these ones, so it's 10 times 10, so 100 times. Doing 100 iteration is pretty fast, but then when we come up to 100, we now have 100 times 100, so it's 10,000 iterations. So you can see how it grows very quickly. So instead of doing this, we could use the modulo operator to make the time of this linear. They were saying that if we double the number, we will double the amount of iterations. by doing this, we can create another solution where is let I equals 0, and as long as I is less than number, if the number modulo I equals 0, we return false. So the modulo operator works in a way that you take two numbers, it does a division, and it returns you the remainder after the division. So saying like the number in this case would be 10, we were dividing it by 5. It evens out by 2, so the remainder equals 0. But if it would be like 10 and the increment would be 3, we would get 3 and the remainder would be 0.3333, repeating of course. So this way we know if there is an even division. When looking at the prime number, we know that there should be no number that's smaller than number that has an even division. So if we find one, it's not a prime number. To save this file, we can see if our theory works out. Of course, this will fail because we are starting on 0 instead of 2, as every number will be evenly divided by 1. And here we go. Now we have it pass. So let's take a look at how we can improve this. We know that we are multiplying numbers together, which means that we only have to look at the bottom half of the numbers, right? Because for this example, if we are in 10, if 10 is the number that we're looking at, there's no number that's above 5 that can be used to construct 10. Would this work for like 18? We could do 2 times 3 equals 6, and 6 times 3 is 18. So we should be okay by just going through the numbers that's lower than half of our target number. I think we need an equal sign here though. And we probably want to round it, just to be safe. And I would like to do a ceiling, just to get it up to the ceiling, to round it upwards so we don't skip a number that we need. And this is like, feel a bit uncertain here, and this is where it's great. So we can try this thing, and we have the test that will tell us if our solution works or not. And we're still matching all the numbers, so we know that this works. And I had a sneak peek at Wikipedia before starting this episode, and they say that we can go even further than this. And that is by using the square root of the number. And if it's not a prime number, we can find all the different numbers or factors we need below the square root of the target number. I'm not sure I can explain how this works, but the math checks out and our test tells that it does. Just to make sure, we could add a test. Make sure our implementation is okay. It returns the prime numbers between, and we can change the index a bit just to make sure we have some different cases. One between 100 and 200. And then we do a similar test where we have primes equals get prime numbers between, and we add our 100 and 200, and then we expect and then we have an array from the internet again, assuming that people don't lie. We can run this test again, and we have an error. Primes is not defined. If we correct our typo, we'll see that it works for these two different cases. And now we can, if we want to get even deeper into this, we can go on the internet, we can look for other alternatives, look at cool algorithms that solve this even faster. I'm sure people have spent a lot of time trying to figure out fast ways to find primes. We have our test suite that's gonna make sure that our implementation still works. Now we just need to hit up the last part of the question, which is we have to print these numbers. Just an index file here with the function body. We'll call directly. We'll import our function. If this looks weird to you, I'm using Node for this example, just to be able to run the test easier and not have to set up Webpack and stuff like that. And this is the kind of imports you use in Node, which looks a bit different from if you're doing them in the browser, but it's the same concept. Then we can go and create our function, print primes up to n. We do define our primes, which are get prime numbers between 1 and n. And then we want to print them in a nice way. Maybe we could do a for each of our array and print one on each line, but that becomes pretty verbose. So let's go ahead and do a console log and then take our array, join them together into a string with a comma as a delimiter. And then in our function, we call print primes 552, for example. We save this, our test route will run again, but if we cancel this, we can do node source index and to run the program, and we'll see that outputs a lot of prime numbers. And that's it, folks.